Here we see the pre-built subassemblies with which we will demonstrate stress variation on a layered beam due to a pure bending load. For this demo, we have built two beams of equal cross-sectional area and length. Each beam is made up of 3 layers. One beam has steel assigned to be the material for the top and bottom layers, and aluminum to be the middle layer. The other has the reverse. Aluminum makes up its top and bottom layers, and steel makes up the middle. We will run the models to compare the results of stress due to the same bending moment applied to both beams. As in the previous beam demonstrations, each subassembly consists of the beam, a part used as a tool to apply the load, and a block on which the constraints are applied. This demonstration model is different in that each beam is made up of 3 distinct solid parts which are assigned the different materials. These 3 parts are glued together, and each beam is glued to the tool and block. For both cases, we apply 2 1-Newton forces in opposite directions on a tool to apply bending to the bars. With the length of the moment arm at 0.10909 meters, this translates to a bending moment of 0.218 Newton meters acting on both bars. The model is now ready to run. Right-click Assembly on the model tree and select Set Analysis Context. When Apex reports that there are no offenses identified and that the current analysis context is ready to be submitted to the solver, proceed to run the analysis by clicking on the yellow running man at the bottom of the window. Now that the analysis is completed, let's take a look at the results. Click on the Post tab, double-click on Scenario Assembly. In the Model subsection, we hover over the visibility icon on assembly and select the empty box to hide all the parts in the sub-assembly. Next, we look at the steel aluminum steel subassembly. We hover over the steel top part, aluminum middle part, and steel bottom part and click on the check on each one. This will display just the steel aluminum steel composite beam. We press both buttons on the mouse to fit the model to the screen. The deformed plot of the part will now display. To show the fringe plot of the stresses, we click the fringe icon. If we hover over the area of the spectrum, we see that we are viewing von Mises stress. Let's change this to X component. To get a better view of stresses within the beam, we change the FEM render style from wireframe to hidden lines. Here we see that the top of the beam is in compression and the bottom is in tension. More importantly, we see that the stress gradients within the bars of different material on this composite model corresponds with our hand-calculated plot of position versus stress. Now we hover over the visibility icon on assembly and select the empty box to hide all. Next, we look at the aluminum steel aluminum subassembly. Hover over the aluminum top part, steel middle part, and aluminum bottom part and click on the check on each one. This will display just the aluminum steel aluminum composite beam. We press both buttons on the mouse to fit the model to the screen. As with the steel aluminum steel composite, we see the deformed plot and the fringe plot. Since it is still showing X component of stress, here too we see the stress range showing the stress gradients on each part of different materials. Notice the high gradient on the steel middle where we see the maximum and minimum stress occur as we predicted on our closed form solution and our graph. Now let's show both composite beams together and compare their deflections with the closed form solutions. We change the quantity in the form from stress to displacements translational resultant. As we can see, the aluminum steel aluminum beam deflects much more than the steel aluminum steel beam, which correlates to our calculations.